Functional analysis builds a geometric engine out of the abstract rules of vector algebra. This engine is the normed space. In 1922, mathematicians like Norbert Wiener and Stefan Banach independently realized that solving complex problems in analysis required formalizing the environment those problems lived in. The framework is a specific combination of parts. You take a vector space for algebraic operations, add a norm to measure length, and the result is a normed space. If that space has no missing points, it is a complete Banach space. This structure ensures that vector operations are continuous. If you nudge an input vector by a small amount, the resulting sum only shifts proportionally. The geometry stabilizes the algebra. Seamlessly binding these two fields allows mathematics to handle limits safely, provided the space itself is complete. In a normed space, an infinite series is a path of vectors laid head to tail. We define absolute convergence by measuring each vector's length. If that total sum is finite, the sequence should theoretically have a destination. However, a finite path length does not guarantee that the destination exists within the space. In an incomplete space, the series can lead to an empty gap in the coordinate plane. A Banach space solves this by ensuring all gaps are filled. It guarantees that every absolutely convergent sequence will always land on a solid limit point. To navigate these infinite-dimensional environments, we use a Schauder basis. Instead of finite sums, we use infinite series to approximate complex target vectors, with each added term reducing the error until it hits zero. As we scale up to infinity, standard algebraic guarantees disappear. Without the strict safety net of completeness, infinite series become mathematically unpredictable. Lemma 2.41 provides the tool to manage this complexity. This inequality establishes a lower bound, relating the total norm of a vector sum to the sum of the absolute values of its coefficients. The inequality prevents independent vectors from perfectly canceling each other out. The total length of the resulting sum cannot hit zero unless the scaling coefficients themselves are also exactly zero. This creates a rigid logical link. If a sequence of these vectors is Cauchy, meaning the total sum is shrinking towards zero, the inequality forces the numerical coefficients to shrink as well. The vector sequence effectively traps the scalar coefficients, forcing them to form a Cauchy sequence of standard real or complex numbers. Lemma 2.4-1 ensures that vectors cannot collapse into nothingness, directly linking the behavior of complex vector sequences to the simpler, predictable convergence of numbers. These mechanics lead directly to Theorem 2.4-2, the guarantee that every finite-dimensional subspace of a normed space is mathematically complete. Because the non-collapsing lemma establishes a floor for the total length of a vector sum, a shrinking sequence of vectors leaves the scaling coefficients with nowhere to go. They are forced to form Cauchy sequences themselves. Since real and complex numbers are inherently complete, those coefficients must converge to a value. Those values then define the coordinates of a guaranteed limit vector, proving the subspace is solid. We have established three definitive rules. Vector operations are continuous, absolute convergence requires a Banach space, and finite dimensions are always complete. The counterintuitive behaviors of functional analysis remain strictly in the domain of infinite dimensions. Within any finite framework, the standard rules of algebra and the geometric rules of normed spaces exist in total alignment.